Hello, everyone. Welcome back to another Keep Looking Up with the Ward Beecher Planetarium. I'm Tiffany Woolbrick, and I'm here to bring you guys, along with our team, our whole crew, our show tonight, all about black holes. Let me introduce you to Kurt Spivey, our engineer.
Hey, everybody.
And Elaney.
Hello.
Nishan and Jenny.
Hello.
Hello.
We are going to start off tonight with a little look at our current nighttime sky with Kurt, and move on from there with some talks about black holes. Please, if you have any questions as we go along during Kurt's Star Talk or anything, if you have any questions that you've been wondering about black holes, go ahead and put those in the comments so we can have some dialogue going, because I'd love to answer your questions about this really wonderful topic, very interesting topic. We have a link down below to sign up for our mailing list if you're interested. Once a week, we send out an email to those on our mailing list that give information on any upcoming online events that we have or programs that we've developed for online consumption. Or you can just follow us on YouTube, Facebook, Twitter, whatever's easiest for you. But if you like that convenience of a once a week email, please sign up to that newsletter. Without further ado, are we ready to get started? Thank you, Kurt.
Yep. So, you're ready for me just right off the bat. Okay, great. Well, welcome, everybody. This is a while since I've done this particular Star Talk. This is going to be very similar to what we did in the Planetarium. What I am going to do right now is share my screen, like so, and minimize that. And then I am going to go full screen on that. I think. Hold on just one second. Got to do one thing here. Like that. There we go. Okay. So, why is Hercules up? This is live in action here. I think I need to do that. Yes. Okay, there we go. All right. So I have a set for tonight here in Youngstown. This is 10 o'clock this evening. That has to do with what I'm going to do with my star talk a little bit later. But we are starting facing south. And I know tonight we've got a few clouds out there. Tomorrow night's going to be kind of cloudy too. But we have some clear nights coming up that you'll be able to get out and see these things. I started us in the south because we have 3 objects of interest. First, over in the southwestern sky are Saturn and Jupiter. These guys will be due south just as the sun sets at 7 o'clock. There'll be more over in this area. Jupiter is the brightest thing in our evening sky right now. Saturn is also very bright. And they'll set by about midnight tonight. So you have the hours to see that. The most important thing down here tonight, though, is right over here. On October 6th, we had our close approach to Mars. We were only 39 million miles away from Mars. It's the closest we'll be to Mars until the year 2035. But the 12th, 2 days from now, we will be at opposition with Mars. That means Mars is opposite the sun in our sky. It'll rise as the sun sets. It'll be up all night long, and it will set as the sun rises. So Mars is at its brightest right now. Even if you have a medium-sized telescope, it's close enough you can actually make out features on Mars right now. So if you get a clear night, I encourage you to do that. Even a pair of binoculars and a small telescope will give you a good view too. So those are all down in the south. But now we are going to talk constellation. So I'm going to move us around so we are in the northern sky. And I do have the light pollution on. That's what all this glow and fog is down here on the horizon. We're putting up with lights in the area. And we're going to look at first how you can find your way in the north. That is these 3 stars here make a handle. These 4 stars make a cup. And for all you planetarium veterans out there, you probably recognize that. That, of course, is the Big Dipper. And if I click on a star down there, I can do that. It's part of a much larger constellation that we call Ursa Major, the Big Bear. And I forgot to do something, but let me see if I can do that and get rid of that. Nope, that makes it do the whole thing. We'll try that again. No, that didn't work. That got it. Okay. Anyway, so what we're going to do is take these 2 stars at the end of the Big Dipper's cup. We're going to draw a line from the star at the bottom of the cup through the star at the top of the cup, follow that across the sky. And when we do that, we're going to hit this bright star right here, which is called Polaris. And I got to remember how to do that again. Nope, that isn't it. Polaris is the North Star. It's always at that spot in the sky, so it's very easy to see in the nighttime sky. It's in the Little Dipper, which I had up there briefly, and I'm going to get a little closer. That makes it easier. And the whole sky appears to rotate around this one point. You've heard this with all the star talks we've done with these things, so I'm not going to go much into that tonight. But since it's always there, it can always tell you north, so it's right there. Now, because the Big Dipper is so low in the sky here, it can be tucked in behind some trees or some buildings from your point of view at this time of the year. This is as low as the Big Dipper ever gets in our sky. It's always up there, but it is pretty low in our sky right now. Fortunately, we have a stand-in that can help us find the North Star as well. If we go past the North Star, hang a little bit of a right, there is a very, very distinct W shape in the sky over here. I'm just going to click on a star and you'll see it's an M or a W. This is a constellation known as Cassiopeia, the Queen in the nighttime sky. And we're going to be talking about her. in our star talk coming up a little bit later. But you notice in Cassiopeia, this side is pretty steep and this side is pretty shallow. If you go to the steep side of the W here and you draw a line from the star at the bottom through the star at the top and curve it just a little bit, that also will point you right over at the North Star. So since, and Cassiopeia is very much like the Big Dipper. You can see that when you're around light pollution, and she also is always up in this part of the sky. Now we're going to come around to the eastern sky, and this is why I set us for 10 o'clock tonight. We are actually looking at the fall sky over here where Mars is. And when you're looking at the fall sky, you're actually looking up and out of our galaxy. You're looking perpendicular to the plane of our galaxy. So there's not a lot of really bright stars or, you know what, something else I'm going to do here. 1 second. I am going to get rid of that light pollution so we can see a little bit better. That's more like it. When you look up here at the stuff in this part of the sky, oh, my star names are back. The Milky Way is running right in through here, but there's just not a lot of really bright stars or easy to identify constellations in this part of the sky over here. But I do enjoy the fall sky for a number of reasons. First off, fall, you get days like we've had for the past 2 weeks. The evenings are cool. There's not a cloud in the sky. You get a very good view of the sky, but it's still warm enough that you can get out and spend some time outside and still see things in the nighttime sky. Second reason I like the fall sky is back when they created constellations a long time ago, they used them for a lot more than just remembering where stuff was in the sky. Constellations were used to teach moral lessons to people of the time, but probably the most important thing was they were entertainment. People didn't have TV or the internet or the Ward Beecher Planetarium for entertainment. They'd go out and lay on a hill at night and look up at the stars, and they'd make up stories about what they'd see, and they'd tell it to a bunch of people. That was their entertainment. Well, it just so happens there is a story that goes along with most of the fall sky. And you might have even heard of it before if you've ever seen a movie before called Clash of the Titans. Now, I'm not talking about that train wreck that came out about 10 years ago. That was just awful. I'm talking about the one that came back out in the early 80s. It had really cheesy special effects. It starred people like Burgess Meredith and Ursula Andress and Sir Laurence Olivier, whom most of my younger audience probably has absolutely no idea who I'm talking about. But if you know the story of Clash of the Titans, it will kind of relate to the fall sky. The other reason I like the fall sky is I have already shown you how to find most of the characters in the story. The Big Dipper is down here now, and that line we drew up to the North Star is what we call a star hop. And if we just keep that line going, we'll run into most of the characters in the story. For example, if we go just past the North Star, we're going to hit this star right here. And we find that in a constellation known as Cepheus the King. He looks like an upside down house there. He is the husband of Cassiopeia, the queen in our story right there. So that is our king and queen in our story. If we keep going past Cassiopeia and hang a little bit of a left, in this particular software Stellarium that we are using tonight, it doesn't look that much like a square, but right here is the most prominent pattern of the fall sky. It is called the Great Square of Autumn. Go figure. Now, if you are at a very dark location, I can help you picture this as something a bit more familiar, considering what's going on right now. There's home plate, first base, second base, and third base. If you look carefully, you can see the pitcher is having a conference on the mound with his catcher right there. The umpire is back here waiting for play to resume. The next batter is waiting over here on deck for the play to resume. And you can tell the team out in the field is really scared of what he can do. Look at all these guys that's stuck in the outfield. What do you bet? They're all stars. Yeah, yeah, yeah. Okay, puns don't work on the internet. I gotcha. Anyway, as you can imagine, the ancient Greek people did not play baseball, and there is not a story, and there is not a character in our story called Great Square of Autumn. These four stars are actually shared by two different constellations. The square itself is the main part of Pegasus, the winged horse. Now, this is the line drawing. As you see, it's drawn as half of a horse. Here are the legs, here are the here's the head. Out here is supposed to be a wing of a horse. And I tell you, if I get rid of that thing, I cannot see a horse up in this part of the sky. So for the sake of the story, when I talk about Pegasus, I'm just going to show you the square. That's good enough for me. If you found the square, you found Pegasus. This star over here, though, is shared between Pegasus and another constellation. Doesn't look like much here, but this is the daughter of Cassiopeia and Cepheus. Let me just do that and that. So they're up there too. This is Andromeda the princess. So we'll get to him in a minute down there. There's two ways you can picture Andromeda. One is to picture this star as her head, and her name begins with A. So one side of the A comes down like this. One side of the A is right there, and the cross piece is right here. Now, before I show you the other thing, I want to show you this little fuzzy smudge that is right here at the cross piece of the A. If I zoom in on that, you'll see that that right there is actually the furthest thing that you can see in the nighttime sky without the use of a telescope or a pair of binoculars. That is the nearest large galaxy to our own Milky Way. That is the Andromeda galaxy in the nighttime sky. And that little smudge of light in the sky is 2.7 million light years away from the Earth. So that's really cool. You'll be hearing more about that in a future show, by the way. So I won't go too much into it tonight. But the other way you can draw Andromeda is this star is her head. Let me see. So I'm not used to doing this on the software. I'm used to doing this in the planetarium. Let me back it up a little more. These three are her body. One leg is right here. Her other knee is right. Her other leg is right there. Her knee is bent at Andromeda. She is reaching out like this, and she is chained right here. And here's her other arm, and she is chained right here. Well, why is Andromeda chained? That goes to our story, and our story actually begins with King Set. Whoop, I did it again. Actually begins with King Cepheus and Queen Cassiopeia. Now, when you see these two constellations in the nighttime sky, you will notice that Cassiopeia is much, much brighter than Cepheus. And that's pretty much how it was in ancient Ethiopia, too, where these two ruled. Here's the real brains of the outfit here. And for the most part, Cassiopeia was a very good ruler. She took good care of her people, and the country prospered. However, she did have one drawback. She liked to brag all the time, and her favorite thing to brag about was her very beautiful daughter Andromeda in the nighttime sky. But one day she was going on about how pretty her daughter was, and she went too far. She said Andromeda was even more beautiful than the Nereids. Now, in order to make these stories entertaining, a lot of times they did get rather ridiculous. And we have reached the first ridiculous part of our story, because basically a Nereid was a mermaid, a half woman, half fish. These were the servants of the god Neptune, the god of the sea, or the god Poseidon, if you're sticking with Greek. I tend to use the Roman ones, Neptune, because of the planet. And they overheard Cassiopeia say this. They're like, where does this mortal get off saying there's another mortal more beautiful than we are? We're really insulted. Hey, Poseidon, do something about this lady. So to teach Cassiopeia a lesson, Poseidon sent Cetus the sea monster to Ethiopia. Sea monster, ridiculous concept number 2. Now I'm bringing this around. You can find Cetus in the nighttime sky. However, He was designed to be a sea monster, kind of mysterious, kind of down below the waves. So he is rather difficult to find, even if you know where to look for him. But if you're standing on first base here and you steal second base, you'll go through a hunk of the sky where there's hardly anything at all. When you start hitting the stars again down here, this is Cetus the sea monster down here. Now, Cetus comes from the Latin word cetacea, which of course is the scientific term for a whale. So sometimes this is drawn as a whale down here. Let me get this out of the way here. You'll see this is a lot of really faint stars down in this part of the sky. But according to the Greek legend, Cetus had the head of a dragon, the paws of a lion, and the tail of a fish. And if you can get that out of these nothing stars down here, congratulations, you have the imagination of a Greek person. So anyway, Cetus went to Ethiopia and he began to make life miserable for the people who lived there. He began to wreck any ships that came near the shore. He snatched people off the beaches. He destroyed whole towns, and nothing was being done about this. Finally, the people got fed up and they went to their king Cepheus and said, hey, you got to do something about this sea monster or we are not going to have a kingdom left. We're all going to leave. So Cepheus asked Poseidon what to do. Poseidon told him the only way that Cetus the sea monster will go away is if you offer your daughter Andromeda as a sacrifice to the sea monster. So King Cepheus and Queen Cassiopeia dragged their poor daughter Andromeda down to the seashore. They chained her to a rock and they left her there to be devoured by Cetus. That's part one of our story. We'll get back to that in just a moment. Part two of our story, though, involves a hero, and his name was Perseus, played by Harry Hamlin in the original movie. Told you wouldn't recognize any of the names. Anyway, there are two ways you can find Perseus. One is if you can see the Milky Way through here. Here sits Andromeda. Just move right down the Milky Way. He's the next constellation in line right here. But if you can't see the Milky Way, notice in Andromeda, there are four fairly bright stars in a row. 1, 2, 3, and 4. And he sits right off that fourth bright star there. And this is their drawing here. He's a little bit easier to see than that. You can kind of picture him as, I'll get rid of that, kind of as an arrow here. But these four stars are his head. These four are his body. He's got 1 foot right here. 1 foot right here. One arm is right here. He's got a sword in his hand right here. And this is his other arm. He's got something in his hand over here I'm going to get to in just a second. But Perseus was a hero, so he went around doing heroic things. And in the process of doing so, he made friends of some of the gods and enemies of other gods. Well, one of the gods didn't like him very much, gave him a job he had to do. He had to go kill Medusa. And you've probably heard of her before. She was the woman with snakes for hair who was so ugly.
How ugly was she?
Not too bad. We practiced that a couple of times, but you get the idea. She was so ugly that when anyone would look at her, they would immediately turn to stone. So we just ratcheted up the ridiculous meter a couple of notches. Anyway, other heroes had gone before Perseus to try to kill Medusa, but when they went into her lair, they looked around for her. As soon as they saw her, they turned to stone, and it's awful hard to kill somebody when you're made of stone. So things did not look too good for our hero, but it just so happened that one of the gods that did like Perseus was in charge of all the other gods, and that was Zeus. So to help Perseus on his quest, Zeus gave him two very special things. One was a sword. Well, I zoomed in. One was a sword that was so sharp it could cut through any material without ever becoming dull. And the other was a shield that was so polished it was like a mirror. Well, Perseus was a pretty smart guy. So when he went into Medusa's lair, he didn't look around for her. He watched in that shield for her reflection. By seeing her reflection, he did not turn to stone, and he was able to use that sword to lop off her head, and that's what he has in his hand here. Those 5 stars are the head of Medusa. Now, this is by far the silliest part of this story. It's also the grossest part of the story because when somebody gets their head lopped off, there's a lot of blood involved. We'll just leave it at that. But according to the Greek people, the blood of Medusa flowed down to the seashore where it mixed with the sea foam, and springing forth from the sea foam and the blood of Medusa was Pegasus, the winged horse. How? I have absolutely no idea. But anyway, Perseus put Medusa's head in a bag, hopped on the back of Pegasus, and they began to fly back to Mount Olympus so he could present the head to the god who gave him test. So he completed it. Well, in the course of flying back to Mount Olympus, did that again, Perseus and Pegasus happened to fly over Ethiopia. And they look down, what they see? Poor Andromeda chained to that rock, and Cetus the sea monster just about to eat the poor girl. Well, Perseus took one look at the very beautiful Andromeda, fell in love immediately, and since he was a hero, he decided to do something heroic. So Perseus had Pegasus swoop down over Cetus the sea monster, and he took Medusa's head out of the bag and held it up really high. Now, even though she was just a head, she was still pretty ugly. Cetus took one look at the head of Medusa, turned to stone. The hero got the girl. The story had a happy ending. Well, almost, because there was still one group of people who weren't too happy, and those were those Nereid mermaid fish women things. So they were still upset because Cassiopeia was getting off scot-free for insulting them. So the reason Cassiopeia's constellation shaped like a W, this is her throne. The back of the throne is here, seats right there, and there's the footrest. And for bragging all the time, the gods condemned her to all eternity to hold on to her throne for dear life as it whipped around the North Star once a day. Or as one of my kindergarten teacher friends says, she's in an eternal timeout for bragging all the time. So that's the moral of the story. You shouldn't go around bragging all the time. That's one reason they told the story. Second reason they told it was the entertainment value. I hope you can see it after my little shtick there. But the third reason they told the story, and the reason you guys can remember it, is now by knowing that story, you know Cepheus, Cassiopeia, Andromeda, a couple other ones that you don't need to know there, Pegasus, Cetus, and Perseus. 6 constellations in the nighttime sky. Now, by knowing that story, I don't mean you should try to memorize that story. That's rather beside the point. But what I hope you will do, though, is the next time you're outside and the stars are out, you'll go up and take a look. These things are going to be in our nighttime sky and actually getting higher and higher and earlier and earlier over the rest of the month of October and into November. There's always something to see in the nighttime sky, and I hope that gives you a starting place where you can go out and explore it. And in our comments section, you will see a link to a sky map. Skymaps.com. You can print off a PDF to help you with your search. And of course, we hope to be able to help you back at the planetarium sometime again soon as well. With that, I'm going to stop sharing my screen, and I'm going to turn you back over to Tiffany. And always, as we say, keep looking up.
Thank you, Kurt. Entertaining as always. I love that story, even though I have some issues with it. Like Medusa gets a bad rep, but that's another story for another day.
Well, you got to have a villain, you know?
Yeah. Yeah, that's true. So next, we're going to transition to our talk about black holes. Let us know in the comments. Let us know where you're coming from, especially if you're not from Youngstown. We'd love to hear from you. And please ask any questions you have about black holes as we go through. But for the first part of our black hole discussion, Jenny is going to lead that and introduce us to black holes. Jenny?
Hi, everybody. It's time, no offense, Kurt, but it's time to get to the meat and potatoes of our discussion here. Black holes are something I'm very interested in and have been for a really long time, and I hold them close, dear to my heart. Even though that might be dangerous to have a black hole close to you, it's just metaphorical, so don't worry. So let me share my screen here. 1 second. Okay. Alrighty. Can we see my screen before I move on?
We can see it. Looks great.
Alrighty. So we know black holes are some of the most mysterious objects, right? And they're a very popular choice for like science fiction novels, movies, and TV shows. So at least in passing, most of us have heard about them at least once or twice, right? So what are they actually like and where do they come from, right? Well, over the past 100 years, we have made significant progress in answering these questions. Einstein and another theoretical physicist, Carl Schwarzschild, started this in 1916. We all know Einstein for many reasons. His work with his theories of general and special relativity kind of built the foundation for discussions about black holes or very massive objects with very large gravitational pulls. So as an object has more mass, if its mass increases, it gets increasingly more difficult to escape the gravitational pull of that object, right? And here's Schwarzschild working on his stuff, right? So eventually, if an object gets so massive, the gravitational pull is so strong that one of the fastest things that we know of, light, cannot even escape this gravitational pull, which is insane, right? So light travels about, here's a cool GIF that I found. Light travels about it's like 3 times 10 to the 8th meters per second, right? But let's put that into our perspective, right? That's like 186,000 miles per second. So as you can see here, that light can orbit the Earth 7.5 times a second. And that's pretty fast. So we can kind of assume that the mass must be enormous for black holes. If it has such a strong gravitational pull that something that's moving that fast can't even escape. So there is a threshold in which this happens, and we call it the event horizon, as you can see here, right? And in layman's term, the event horizon is basically the radius from the middle of the black hole in which, or the massive object, in which the light cannot escape. And this radius was part of Schwarzschild's solution to some of Einstein's problems in his works with general relativity. So sorry. Oh no, I'm going too fast. Okay. So for example, and we want to talk about the Schwarzschild radius a little bit, because that sounds kind of weird. Anything can have a radius, a Schwarzschild radius. For example, let's say the Earth. The Schwarzschild radius of the Earth is about 1 inch. So if you took the entire planet and you smushed it, you squeezed it so small to the size of about a ping pong ball, then it would have an event horizon, because it's all of that mass of the Earth, but in a very, very small space. So then its gravitational pull would be enormous. So it would have an event horizon where the light couldn't escape. So as time went on, Princeton University became the lead center for research on Einsteinian gravity. And this man, a theoretical physicist known as John Wheeler, innovated the research of gravity because he leaned towards a more experimental approach instead of purely theoretical. So Wheeler is sometimes referred to as a local to Youngstown. He was born in Florida, and then he studied physics and mathematics here in Youngstown. And he later moved on to Princeton and the University of Texas for further research. And he was really popular for his work with some of his students, including Richard Feynman. His work with Richard Feynman led to a Nobel Prize, right? So they worked to revive the field of gravity, right? And one thing that was very puzzling to them was the idea of a singularity. And we have this shown here. Basically, the center of a gravitational well, which is this part around here. So the singularity would be the center of this extremely massive object where the light couldn't escape. Their hypothesis was that a star or something that was extremely massive would collapse in on itself because its mass was so large. And if it collapsed into itself, there'd be so much mass, it would, it's kind of hard to explain, let me see. If it collapsed on itself with all this mass, it would be a very small space with all of this massive stuff, right? So it would continue to collapse in on itself until it was so dense that space itself would warp around it. So it would be infinitely curved and infinitely massive. And that's what a singularity is. And that didn't make sense to Wheeler. He rejected it at first. So we perceive the world based off of what we see. And if light can't escape from a singularity and everything is warped around it, then we can't see them. And he was describing this at a conference in 1967. And somebody in the audience mentioned the term black hole. And since it fit so well, it stuck. So there's I guess it's a misconception as people saying, John Wheeler coined the term black hole. He popularized it. So I guess we'll never know who that student or person was in the audience who coined the term. So talking about singularities started a new field of gravitational research. It kind of revived the field of study. So what are these mysterious objects and do they actually exist? You know, they were asking this at this point in time. So yes, in theory, it was possible that they could, even if it was absolutely absurd. And over the next 50 years, theoretical physicists would make some progress learning about these. So, and here is, here's another picture of John Wheeler. So as a black hole, just a black hole, are there different types? Are there different sizes? And how do they form? Where are they? Okay, so over the past 50 years, we're talking about how science, over the past 50 years, they're working on this. And science has revealed that most black holes are a result of a large star who has had better days and ends its life in a supernova, right? But only large stars, typically about 5 times the mass of our sun, can go supernova. And this is pretty spectacular, but terrifying. So here's a good diagram that I found that shows the life cycle of some giant stars, right? So they can take different paths, right? But most of the time, if they have enough mass, they will turn into a black hole or a neutron star, which are incredibly dense objects as well. So what happens during a supernova is that the pressure caused by the large star, all of its fuel is being burned on the inside with nuclear fusion. And it creates pressure on the inside of the star. Yet it's so massive that the gravitational pull is pulling it inside. And that's what keeps them spherical and keeps them stable, quote unquote. So eventually that fuel for fusion, it diminishes it, or it will completely use all of its fuel. And the pressure from the inside of the core doesn't exist anymore. So the entire star's gravitational pull will take over and it'll collapse in on itself and then it'll go supernova. So here's a cool GIF that I found that shows what a supernova may look like. So I'm going to go back here. Okay. So what's left are the remnants, right? So we're talking about black holes. It could become a neutron star. But when it does create a black hole, it'll collapse so far down and suck all of the surrounding objects into it, and it'll continually get more massive. So that being said, there are different size black holes. So we have, let's see. Okay. So there are different sizes of black holes, right? We have stellar, which are smaller black holes. They're still large, right? That's 1 to 100 solar masses. So 1 to 100 times the mass of our sun. Then we have intermediate black holes, which we didn't know about at first. And then we have the big guys over here, supermassive black holes, right? And these are usually at the center of galaxies. So we actually have one in the middle of our galaxy, but don't worry, it's not going to come get us. It's called Sagittarius A, and here's a picture of it. Well, as good of a picture as we could get, that is. So let's go back to here and talk about these types of black holes. So the stellar black holes are very small compared to the supermassive black holes, right? So I was looking up some facts about these, and I found, according to the Harvard-Smithsonian Center for Astrophysics, that the Milky Way, our home galaxy, may contain a few 100 million stellar black holes. So that's a lot. But you have to remember that the galaxy is very large. So I don't think we have to worry about them being too close to us. So we're going to talk about supermassive black holes. And I found this really cool GIF that shows exactly, well, it tries to show how large these things actually are. So we have our sun here, and it's laying out how many solar masses are in this black hole, right? And there are billions of them. It's just insane to think about how many suns fit inside this very, very small space. All right. And here I found a good representation of how objects would move around black holes. Okay, so now that we know a little bit of history about black holes, how do we know if they're there if we can't see them, right? Light can't escape. So how do we view them? Well, we can't observe black holes directly for obvious reasons, but we can notice how other objects around them interact with it. So to talk about that, I'm going to give it back over to Tiffany.
Thank you, Jenny. Wow. Sorry, I was reading some of your comments. Thank you, Jenny. I think that it was really interesting the comparison of black holes, and as Jenny was saying, we do have many stellar-sized black holes in our galaxy, our Milky Way galaxy, but none of them are anywhere close to Earth. And our sun is nowhere near the size it would need to be to supernova. So Earth is safe from any black holes. But it's really fascinating to know of their existence and to especially that supermassive black hole in the center of our Milky Way galaxy that we call Sagittarius A star. I'll be talking a little bit about that as we transition here. I'm going to share my screen and just start with some basic parts of a black hole to try to help us conceptualize this really complicated and exotic sort of feature of physical space. And you saw a picture similar to this with Jenny's presentation. What you're seeing here with the cone shape is representing space-time. So if you think of space going in one direction, time going in another, and it creates this sort of plane, this like fabric, then gravity would weigh down that fabric. So a black hole would have this really deep sort of well shape. And this is just kind of a way to conceptualize both the gravity's mass and both the black hole's mass and its immense gravity. So what we have here is the singularity, which is what Jenny was talking about. It's sort of the center of the black hole where its density is infinite. Space-time curvature would be infinite. Basically, the laws of physics that's sort of the limits of how we understand the physical world. So then you have the event horizon. The event horizon is the point at which nothing can escape the gravitational pull of the black hole, not even light itself. So in these these photos that you see of black holes where there's a big black hole in the middle, what you're seeing is the event horizon. You're not actually seeing the black hole. And again, these are all kind of renders because up until very recently, we have not photographed a black hole. It's black and it's incredibly difficult to observe directly. After the event horizon, we have the ergosphere, which John Wheeler also helped name this part of a black hole. It's pretty cool that we have such a famous and successful scientist that studied here in Youngstown, right in our town. John Wheeler really was responsible for getting gravitational physics kind of back in the spotlight and helping popularize black hole, the term black hole, as Jenny was saying. So the ergosphere is, it's really just this a spatial metric component. It's really just sort of a way to it's like think of it like the yellow zone. Like you don't want to be that close to a black hole. If you're in this green zone here, this quiet region is what they call it, you're good. You're negligible gravitational influence. You'll be okay. If you start getting the ergosphere, you're going to start feeling the effects of the black hole. So that's just sort of a example. I wanted to mention this type of black hole because it's something that we can observe. It's kind of rare, but it's really cool. So Jenny mentioned the stellar sized black holes. Well, this is an example of a stellar black hole. This is not an actual photo. It's a visual representation of Cygnus X1, which it formed from a supernova, so from a massive star that caved in on itself. And this black hole pulls in matter from a nearby star. So it was a binary star system. One of the stars supernovaed. Now it created this black hole, and the black hole is being fed by this blue binary star. This is how black holes grow. They like eat, I guess is the way to think of it. They eat mass or matter. Anything that comes near them, they gobble it up and you'll never see it again. And the mass of whatever that is, a star, a planet, anything, it would be added to the black hole. So another thing I wanted to mention about black holes is that they're really mysterious and exotic, but I think one interesting thing about them is that we really can only characterize them in 3 ways. So there's only 3 ways that we can characterize them in physical space. We can determine their mass, we can determine their location, and their charge and or their spin. So black holes can spin. So are they spinning, in one direction or in the other? That's it. That's all we can really say about black holes with all the studying that we've been doing. That's all of the characteristics that they present to us. It's the only clues that they tell us. So, and again, because they're black, you can't see them. So we have to detect them indirectly by watching stars, for example, orbiting around a black hole. So they haven't gotten into that event horizon. They haven't been sucked in to the black hole, but they're in some sort of gravitational orbit around it. And that's what you're seeing here with this GIF. These are actually stars in the Milky Way. This is one of the methods that scientists use to prove that there was indeed a supermassive black hole in the center of the Milky Way. That was a debate for quite a while. So you can see there that those stars are orbiting something. Something is causing them to behave that way. And that's how we determine things like the mass and position of black holes, not by observing them directly, but by observing the things that are in orbit around them. So I want to talk a little bit more about the way that we study black holes today, because this is a kind of a new area of astronomy, and we really had to use cutting edge technology to understand and learn more about black holes. Oop, let me go back. So this is a picture of ALMA, which is a radio observatory in Chile. The best way, the way that we often observe black holes is using radio light. So it's light that we can't see. It's radio waves, but it's still electromagnetic radiation, just like visible light is that we can see. But it allows us to do things like look through the dust of the Milky Way. So it's really common for in astronomy to observe the universe in different wavelengths and different areas of the spectrum that our eyes might not be able to see, but is still emitting light. So black holes, you're able to see really well, or you're able to study that area really well using radio telescopes. And that's what you're seeing here. This is just a handful of radio telescopes in Chile at ALMA. And they actually have 66 of these antenna that you're seeing, because the resolution that you need is limited by the size of your dish. So these dishes, I think, are 12 meters across. And so that can only, your resolution of your image that you're taking with one dish is really limited. But there's this new, very brand new technology that's called spectroscopy, if you're interested in looking it up, where they network multiple antennae together and create a virtual dish, an imaginary dish, where they're all of the antennae are looking at the same part in the sky for the same length of time, taking the same data, but at slightly different positions, so that they create this imaginary dish. For ALMA, they can create a dish up to, I think, about 10 miles wide. So you can imagine going from 12 meters, to 10 miles. So it's like 36 feet to 10 miles, like that. Your resolution power is going to go up quite a bit, but still not enough to take a picture of a black hole. Nowhere near enough. So what we did, I didn't have anything to do with it, but what a bunch of really dedicated scientists did is create the Event Horizon Telescope. This is a international collaboration. These are some of the big partners you're seeing here. It's not even all the telescopes, but we have radio telescopes in Hawaii, in the US, Mexico, of course, Chile, in Europe, and even in the South Pole. And all of these radio telescopes, the world's best radio telescopes, work together to create a virtual dish the size of planet Earth. And finally, we have the resolution power to possibly, maybe, take a picture of a black hole. So I cannot understate the massive effort that this took. Thousands and thousands of people from many different countries had to work together in perfect harmony to make this picture possible. This picture was published in 2018, just a couple years ago. This is the first ever photograph of a real black hole. And it is it's exciting. Scientists said it was boring because it's exactly what they predicted would happen. It's not quite as interesting. So maybe not boring, but maybe not as interesting as they were, because it was exactly what they were expecting. You can see the black region here, that's the event horizon. Okay. And the brighter region versus the darker region here, that is showing motion. So that this black hole has a spin. This black hole, this particular black hole, is located in the middle of M87, sometimes called Virgo A, because it's a galaxy in the constellation Virgo in our sky. And the reason we chose this target is because the galaxy is enormous. It's a spiral galaxy, kind of like the Milky Way, but it is huge and it's really old. The stars are very old. It's not making new stars like our Milky Way is. And in the black hole in its center is just massive. So even though M87, this particular galaxy, is 50 something million light years away from us. I wrote it down so I don't forget. Yeah, 53 million light years away from us. That the black hole in the center of that galaxy was one of the best targets to take a picture of, even a better target than our own black hole in the middle of our own galaxy. Because Sagittarius A star, our black hole in our Milky Way, is about 4 million solar masses. So its mass is that of about 4 million suns. This black hole is 6.5 billion with a B solar masses. So it was a great target and it was successful. The second target, of course, has always been Sagittarius A star, our black hole. We want to see our black hole. We want to see our home black hole. But the Event Horizon Telescope project, the group has not been able to generate an image just yet, but they're working on it. And I think we'll see that at some point. It's difficult because it's not as bright with these radio waves as this black hole. And it's in our galaxy. There's a lot of stuff in the way. So I really love this story because this is the beginning of a new chapter in studying black holes. And it's also a testament to what humanity can accomplish when we set aside our differences and we work towards a common goal. It is incredible that we were able to image a black hole. And so with that, I do want to mention this week in the news, we had, it was announced that 3 people won the Nobel Prize in Physics, and all of their accomplishments were related to black holes. So the prize was split in half between Roger Penrose, who his mathematical calculations showed that black holes were physically possible. We, for a long time, just didn't believe that they were even possible, that they could exist in the natural world. So they were first proposed due to Einstein's general theory of relativity, but people were like, no, that can't actually happen in the real world, and so his mathematical calculations proved that yes, indeed it could. So the other half of the prize will be split between Reinhard Genzel and Andrea Ghez, whose work revealed the black hole in the middle of our galaxy. So they helped discover the Sagittarius A star black hole. And I did want to mention that Andrea Ghez is only the 4th woman ever to win the Nobel Prize in Physics since Nobel Prizes have been given out, I think that was 1901. So 119 years, and she's the 4th woman to ever receive a Nobel Prize in Physics. Really exciting. I think that wraps up what I wanted to talk about. Do we have any questions?
We had somebody ask, will the James Webb or any other future telescope potentially be able to give us a better picture of a black hole?
That's a wonderful question. So we're already looking, they're already looking at ways to further the technology to take better pictures of black holes. There's going to be like a second generation of the Event Horizon Telescope, and the plans are already in works. And that plan does possibly include a space telescope. So if we had a radio telescope orbiting Earth that could work with the telescopes down here, that could significantly improve the capabilities of taking these photographs. Yeah.
I should add a long-term plan for a long time has been put a radio telescope on the far side of the moon where the Earth's radio waves won't interfere with it. So maybe down the road, that might be something they do too.
Yeah. Even if there was a radioscope in geosynchronous orbit, that would still be a huge help. And the plans that they have are, they think that they can have like the second gen Event Horizon Telescope by this decade, which is kind of a big deal when you're thinking about building whole new observatories. Something else I did want to mention with the Event Horizon project, I'm a huge fan. I don't know if you can tell, but it took them about 5 full nights or days and nights of observing to take that picture. And the fact that we had all of the world's best radio observatories, they're busy, they're in high demand. To get them to all look at the same place at the same time for 5 full days to take that data, that's just a huge collaboration effort, truly. Any other questions?
I'm not seeing any more questions.
No one's asked what happens if you fall into a black hole. I thought that one would come up.
Oh, there was a question. Someone asked, if a star gets super hot, then is that how it changes into a black hole?
If a star gets super hot,
yeah.
The way that a star turns into a black hole is through this supernova process. So it has to be really, really massive, a really huge star that will then collapse on itself, and that process creates a point with like such intense gravity that a black hole is formed.
Yeah, it's much more dependent on the mass rather than the temperature.
Temperature, yeah.
Yes.
For example, the Pleiades are not very big stars, but they're super, super hot because they're newborns, but they appear blue because of that. Now, some supermassive stars tend to be hot, but that's not the factor.
No, I mean, massive stars, they can be different temperatures. Like you saw that picture with Cygnus X1 and then the blue star, that was a really, really hot star next to that black hole. It was feeding into the black hole. So the blue star was really, really hot. I actually can't remember what kind of star was there before that created the black hole, but it might not necessarily have been a blue star, which is a really hot star. It's more to do with the mass. Yeah. So, do you guys want to know what happens when you fall into a black hole? I always get grade schoolers asking me this question, and I love to answer it with them. Let's count all of the ways that you can die and wonder which one will happen first. It's dangerous. Don't do it. That's the short answer. So if you were to hypothetically reach the black hole singularity, so that center of the black hole, you would be crushed by the infinite density. and your mass would be added to that black hole. So it'd be just a little bit bigger. But before that, you would be torn apart, even at a molecular level, by a process called spaghettification. I have a nice little picture here. Let me share my screen again so you can see it. So basically, you're stretched out. This is an astronaut falling into a black hole. Oh, no. So he's fallen into a black hole here, and the astronaut's getting stretched in one direction until the literal atoms that make up that are in your body would be ripped apart. So you're stretched out like a noodle. That's why it's called spaghettification. Fun times. I think the term is a lot more fun than the actual process. Do you guys want to add anything to it?
Before you got spaghettified too, the massive amounts of radiation coming out of the black hole would cook you like a boiled egg. So.
Certainly. Yeah, well before. I mean, you'd have to avoid the dangers of space to begin with to get there. So I don't know. Luckily, we're nowhere near a black hole, and it's not like they move around and come and get you. So it's interesting thought experiment.
I will point out, as far as supernova go, I do not know which galaxy it was, but some Earth observatory just saw a supernova go off in a nearby galaxy, but it's the first major one we've had since '87. Oh no, I take that back. There was one in M51 about 10 years ago, but yeah, there's a new supernova in a nearby galaxy. Just came out in the last couple of weeks.
Yeah, so as Ginny mentioned, a supernova can result in a black hole, but more often than not, it actually results into a neutron star. It's pretty rare for a star to end up being a black hole, but they do happen. They happen even in the Milky Way galaxy. Another interesting aspect of black holes is time dilation. We can speculate how people would experience time, both as an observer far away from a black hole and being one near or at the event horizon. And we can answer those questions using Einstein's general theory of relativity. It's pretty phenomenal how accurate his theory can explain these very exotic creatures in nature. So I see a question, do black holes distort time as well? So yeah, that kind of ties into what I was saying. So if you were, so assuming you're indestructible, you have to assume that.
Taller though.
And you're falling into a black hole, and you would not notice really any time effects as you cross the event horizon. But if an observer, someone safely away, was watching you, and they would experience you falling much more slowly. So you could pretend like if there was a clock, if you had a big clock and you were holding it up, that clock would tick much more slowly to the observer. Then for you, it would actually look like it would take you an infinite amount of time to reach the black hole. So you just look like you were stuck forever to the observer. It's weird. Time dilation it's mind-blowing. And I have heard that there is some sort of hypothetical situation where you going near a black hole and then coming back could actually reverse time. So you could actually go into the past. I don't exactly know how that would happen, but I think it's sound within the theory of general relativity.
I spent a lot of time of my quantum mechanics class saying, okay, if you say so. That's kind of what I think about that. So
Yeah, my quantum mechanics class, I was like, okay, we'll just. I know my professor used the term black magic a lot. Like, this is some black magic happens here, and then we're here. It's not intuitive for sure.
Somebody asked, are there any possible connections between black holes and dark matter?
Do you want to answer that, lady?
I can try. I don't believe there are, because in the calculations that have been done that lead us to believe that dark matter exists, the massive black holes are already accounted for.
Well, yeah, that's what I would say is how they're related. Is we suspect that supermassive black holes, which are found in the middle of galaxies, that's common. Pretty much any galaxy that's a decent size has a supermassive black hole. So we assume that those supermassive black holes were formed with their galaxy. And galaxy formation is influenced by dark matter, right? So that's the relation. That's the limit of my knowledge, and I think the limit of most people's knowledge at this point. Dark matter is still a.
Yeah, I think that's all we really know.
speaking of black magic,
we do know that, or we think, based on what we know about the why we think dark matter exists, it exists on the outskirts of galaxies, whereas black holes exist inside galaxies because they form from collapsing stars. So dark matter is kind of not really near where black holes form.
Mm-hmm.
So that's the only thing I know. I don't know if they're related or not.
That's a great question. Speaking of black magic and other spooky things, we like to announce at the end of our shows what our next Keep Looking Up will be. And since we're getting towards Halloween, we're going to have a spooky sky show for October 24th. And we'll start with a star show, and we talk about some of the spooky stories that you can learn about in the nighttime sky, some of the lore and different things. And then we will talk about the outer limits of our solar system. Wahahaha. We'll be talking about the very...
Do not attempt to adjust your Facebook feed.
Yeah.
You control the signal.
Yeah, so come celebrate Halloween or the spooky season with us, and we'll it's going to be a good one. I'm excited. All right, if we don't have any more questions, I guess we'll wrap up. Please ask if you have questions even after the show. We'll follow up with you later in the comments. Thank you all so much for another great night. I hope that you go outside tonight or whenever it's clear again and look up. Good night, everyone. Keep looking up.